Assalamualaikum and selamat sejahtera. So today we will learn about interfacing the ADC. This is our last chapter for our courses. Alright, so in this module 13, okay, you will learn about introduction of the ADC, followed by ADC Programming, and then we look at what is DAC and sensor interfacing. Okay, without further ado, let's look at the introduction first. So ADC, or we know it as an analog to digital converter, are among the most widely used device for data acquisition, in which every time you want to capture a data from real world, you are going to use this ADC. Right? Since the digital computer use a binary, which is a discrete signal, right? So the binary or discrete signal consists of 0101 value. But our physical world, everything is in analog or continuous signal. So in order to process this data here, okay, from the physical signal to computer signal or binary signal, what you're going to do is we need to use this ADC devices, okay, in which you convert from this continuous signal to the discrete signal that only then after that the computer can interpret and process that data, because the computer only know the binary numbers, okay, they do not understand the continuous signals. Okay, those a device called transducer or a sensor is needed to convert physical quantities such as a temperature, pressure, and etc. to electrical voltage current signal. So in order to convert the data from analog to digital data signal, okay, what you're going to do is you need to use a transducer or a sensor, in which this sensor here will convert the physical quantity. Contohlah, if you want to read a temperature, okay, we'll convert that temperature value to an electrical signal, which is sometimes we use a voltage or a current. Okay, in this one is V and this is M. Okay, so after it convert to this electrical signals, either a voltage signal or currents, okay, what you're going to do is then after that we can convert, okay, this analog signal from voltage and M convert to a discrete signal by using the ADC. So first, you are going to use a sensor. You need a sensor which is to convert a physical quantity such as temperature, pressure, velocity, humidity, light to any electrical signals. And then after that, what happens is you can convert to digital signal. So this is the overview of the what we call how to convert from analog signal to digital signal, in which first, in order you're going to read the physical signal by using a sensor. So this sensor here will send your physical signals, right, and then it will convert to here your electrical signal. So this is electrical signal, right? From this electrical signal, okay, next what happen is you need to feed it to the ADC, which is this ADC here will convert this electrical signal, which is your continuous or analog signal here, to digital signal, right? Once the this signal here is converted to digital, the CPU can do processing or data manipulation, and at the end you can display it on your outputs. Okay, so this ADC here actually used to translate the analog signal to the digital signal. Okay, now we are going to see what is the ADC characteristic that we need to know. In ATmega32, an n-bit ADC is used to translate the analog signal to a digital signal so that microP can read and process them. Okay, some of the major characteristics of ADC that you need to know. First is a resolution. Okay, so ADC has an n-bit resolution that varies from 8-bit, 10-bit, 12-bit, 16-bit, 64-bit, 32-bit, depending on the ATmega family that you're going to use. Okay, so higher resolution ADC provide a smaller step size, which is a smaller change can be recognized by an ADC. The smaller the resolution, the higher the accuracy is. Okay, although the ADC resolution is fixed, okay, this one here already been fixed. Okay, if you buy the ATmega32, it is a 10-bit resolution, so you cannot change from 10-bit to 12-bit, but you can change the step size by control your VREF. Okay, so this is how you're going to calculate the what we call here the step size. All right, so for example, you have an n-bit 8-bit ADC. Okay, so number of step is 256. Okay, because 8-bit ADC, okay, can convert from 0 to 255. Okay, for 8-bit kamu ada 0 hingga 255. So total number of step is 256, or sometimes you can put 2 power of 8. Okay, you get 256. Right? So in order to calculate the step size, okay, in order to get the step size, what happens is, okay, so here this is your VREF. Okay, so you're going to, okay, step size, okay, this is the step size sama dengan VREF divided by your number of steps. Okay, in which this VREF is varies depending on what type of voltage reference that you're going to use. Sometimes you use the VCC, sometimes you use the internal voltage. Okay, sometimes you use the VREF. Okay, it depends. Okay, later we'll see which one that we're going to choose. Okay, so this is the formula. Step size sama dengan VREF bahagi divided by number of step, in which the number of step, okay, number of step equal to 2 power of n, in which n is your bit size. Okay, your ADC bit. If you have 10-bit ADC, so the number of step is 1024. If you have 12-bit ADC, so the number of step is 4096. Alright, so then after you apply this formula here, so you will get what is the step size. Okay, so the step size is actually the increment of each of these data lah. Alright, so let's say lah, the first number here is 0000000 0000000 0000001. So let's say this, you started with 0 lah, 0 volt, and then this is 19.53 volt, and then followed by 0 0 0 0 0 0 1 0. So this is the increment. Okay, so 19 cm 3 90.53 90.53, so you get 6 10 19. Okay, so this one here, it is 3906, and it will keep increasing lah by 19.53. So this is the step size actually. Okay, the increment between the first number to the second number, okay, of your binary data here. Okay, so this is a binary, and this is the, okay, so this is the binary value. Okay, and this is your what we call here the decimal value. Okay, next, the second characteristic that you're going to know is conversion time. Okay, so the conversion time is time taken that takes to convert the analog to digital number. Okay, so conversion time depends lah. It varies on from chip to chip. Sometimes it the time is very fast. Sometimes it's very slow to convert from ADC to convert from analog to digital. It depends on the chip. Okay, the type of aggregate that you're going to use. And then the third characteristic that you need to know is the VREF. Okay, VREF is an input voltage used for the reference voltage. Okay, so the voltage connected to this pin along with ADC resolution will dictate the step size. Okay, again, step size, okay, equal to VREF bahagi dengan your 2 power of n number of step. Right, then the fourth characteristic that you need to know is the digital data output. Okay, what are the output, the digital representation of the certain voltage. Okay, in an 8-bit ADC, we have an 8-bit digital data output which is from D0 to D7. Thus, your D out sama dengan V in divided by your step size. Okay, contohlah, your V in that coming to your what we call here. Okay, your V in that coming to your sensor is 2.5 volt. So you are going to find what is the digital output here. Alright. Okay, let's say we take a step size of what we call here of 8-bit. Okay, 8-bit data. The step size, what is the step size of 8-bit is 256. Okay, so D out the step size just now we calculate what is the step size, not 256. We go back. Okay, 19.53. Okay, that is the step size, 19.53 millivolt. Okay, so 2.5 divided by 19.53, so we get okay, let's look at this example here. For an 8-bit ADC, okay, you have an 8-bit ADC with a VREF 2.56. Okay, 8-bit n equal to 8. VREF given is 2.56. Calculate the D0, D7 output if the analog input is 1.7 volt and 2.1 volt. Alright, so you know that D out equal to V in over step size. Okay, so now what you're going to do is you need to find what is your step size, because the V in you already be given. Okay, so this is the V in, and now you're going to find what is the step size. Okay, step size, you know that step size equal to VREF over 2 power of n. Okay, the resolution. Okay, and you will get what is this here, which is VREF is 2.56 millivolt divided with 2 power of 8 is 256, and you get 10 millivolt. So this is your step size. Okay, the step size, each of the bit here is 10 millivolt. Okay, now you're going to find what is the 1.7 volt that will be represented in the digital output. Okay, so D out sama dengan 1.7 divided by 10 millivolt. Okay, you will get 117. So this is in decimal. If you convert to binary, you will get 10, 10, 10, 10, 10, which is equivalent to AA. So this is the digital output of this 1.7 volt V input. Okay, now let's say that you have 2.1. Okay, so D are 2.1 divided by 10 millivolt, you will get 200 tens. Okay, so 210. Okay, you convert this number here 210 to binary, you will get 1101 001. So 13 is get D2. Okay, so this is the digital signal representation or digital out for 2.1 volt input. Okay, next the fifth characteristic that you need to know is the parallel versus serial ADC. Okay, so for parallel ADC, 8 or more pin is dedicated to bring out the binary data, while for the serial ADC, only 1 pin out for data out. Okay, so this is your input. Okay, let's look at this figure. This is your input. You have 8 channel of your input, and this is your output. 8 channel of your output. Okay, so this is parallel ADC, in which the output here will, okay, the output here to represent this binary data here, alright, will be sent out to this 8-bit output. Okay, let's say now the input of your analog is 1.7 volt. Okay, you want to find what is the digital output. So since this you have parallel ADC, so the value of 1010, okay, so 1010, so this D7 is MSB, 1010 will be sent out, okay, directly to your output of this ADC. Okay, if you're going to use a serial ADC, okay, so this is the input. Okay, and while you only have one data out, so what happens is you need to send one data per one time. Okay, but this one 8-bit data can be sent out one time. Okay, so what happens is if you want, okay, your input here is 1.7 volts, so now you're going to find what is the digital output. So what happens is this value 1010, okay, will be sent out to this output. How many cycles? How many times? 8 times. Okay, first you're going to send 1 followed by 0, and then next 1 0 1 0 1 0. So total cycle is 8, but this one here you can send out at one cycle. All the output will send out at one. Okay, and then the analog input channels. Okay, many data acquisition application need more than one ADC. Okay, those ADC chips come with 2, 4, 8, or even 60 channel on a single chips. Okay, if you're going to have more sensors, then you're going to have more ADC input channels. Alright, so the more ADC, the more sensor you can put to your system. And last but not least is successive approximate ADC, widely used to convert analog input to digital input, has 3 main components: successive approximate register, comparator, and controller. Okay, now we're going to see the ADC programming. Before we start with ADC programming, let's look at the ATmega32 ADC features. Okay, you need to know the features, how many bits ATmega32 has, what are the register that you're going to use, and how to do the settings. Okay, so you need to know the, the feature ADC features before you do the programming. Okay, so for Amiga 32, okay, the ADC peripheral has the following characteristic. Okay, so first is it is a 10-bit ADC. So Amiga 32 is a 10-bit ADC, has 8 analog input channel. Dia ada 8 input channel, analog input channel, which is from this 8 here, 7 differential input channel and 2 differential input channel with optional gain of 10 and 200 times. Right? So this one here, you have 8 ADC channels. Okay, I put here, this is a channel. Okay, the converted output binary data is held by two special function register called ADCL and ADCH. Okay, so this is your D out, which is the converted output. Okay, since it is a 10-bit ADC, so the D out here also 10-bit. Okay, which is starting from D0 to D9. Okay, if you use one register only to send out this data, which is not enough lah, because this one you have 10-bit. Okay, for Amiga 32 we only cater up to 8-bit only. So to cater up to 10-bit, what happen is you need to use 2 register to send out this digital output or converted output binary data. Okay, so this one here we call it as a ADCH and ADCL. Okay, so this is the ADCL, consists of 8-bit data, while another 8-bit data coming from ADCH. But the problem is the digital output here only 10 bit. Okay, so let's say like you use, okay, let's say like we use this one here is left justified, right justified. Okay, so use all this data here. Okay, 1, 2, 3, this 8 bit, tambah lagi 2 and make it a 10-bit data. Alright, what about the remaining bits here? Okay, so this 6-bit here will be unused. Okay, this become an unused data because the total bit here is for ADCH and ADCL, or we call it ADC, is 60-bit, but we only use 10-bit, so 6-bit will be unused. Okay, there are 3 options for VREF. Okay, as I mentioned earlier, your VREF can be from your VCC, which is usually 5 word, AREF pin, and the other one is 2 internal reference, which is 2.56 word. Okay, this one you receive 5 here. And the conversion time is detected by your crystal frequency. They are connected to your Estel and this bit here. Okay, so this bit, which is your prescaler option here, will determine your conversion time. Okay, the conversion speed of your ADC, in which you want to convert from analog to digital. Okay, let's recall back our Amiga 32 pinout. Okay, this is our Amiga 32 pinout. If you can see in the port A here, your port A has a special function called as a ADC. Okay, you see from ADC 0 and ADC 7. So this is your ADC input channel actually. Okay, in which we know that the ADC input channel for Amiga 32 is this channel. Is 8, you have 8 channels. So this is your 8 channel, your ADC channel, starting from ADC 0 to ADC 7. Okay, and then while the VREF that you can choose is coming from your VCC, and the other one is coming from your AREF. This is your VREF selection, and satu lagi is coming from your internet, which is 2.56 volt. Okay, so this is how you're going to connect your ADC in order to have a stable voltage source to your VCC pin. Okay, so this is your pin out 30, 31, and 32, which is 32 for your AVREF, ground, and AVCC. So make sure that you're connected to these circuits here, which is consist of inductor and capacitor, so that you can have a stable voltage source. And in ADC 32, there are 5 major resistors that are associated with ADC that you need to know, but we only focus on 4 resistors only, which is your ADCH and ADCL, which is this one here used to store your result after the conversion. This is your D out lah actually. And then ADC SRA, which is ADC control and status register. This one here you will do a settings, okay, for the ADC, okay, in which you, when you want to start your ADC, enable your ADC, enable your ADC interact, etc. And last but not least is your add marks, which is this, we call it as an ADC multiplexer selection register. Okay, this ADC add mark is used to select your VREF as well as to select your ADC channel. Okay, which we have 8 ADC input channel. Okay, so you need to select this which one you're going to use. Okay, if you want going to use, for example, if you're going to connect your sensor to ADC 7, make sure that at your add mark you pilih ADC 7 lah. Okay, so this is the important setting that you need to know. Okay, let's look at the add marks register. So add mark register is a 8-bit size. Okay, in this add mark register you need to know the first 2 bit here, which is bit 7 and bit 6, which is denoted as a ref 1 and a ref 0. Okay, so this ref 1 and ref 0 is used to select your VREF. Okay, so ref 1 and ref 0, which is bit 7 and bit 0, is used to select your VREF. Okay, if you put 0 0 at your bit 7 and 0, what happens is, okay, your VREFs are coming from your AREF. You put 0 1, it is coming from your VCC, which is always 5 volt. And when you put 1 0, the VREF is coming from your internal voltage. Okay, which is 2.56 volt. This is fixed, okay, regardless of your VCC value. Okay, this one depending on the VCC value lah. If you put 10 volt, so this one become 10 volt lah. Sama juga dengan ini. If you 10 volt RF and you selected VREF is 00, which is coming from RF, then the VREF will be 10 volt. Okay, so this is the first two, what we call here, the first 2 bit that you need to know. And then next is this 5 bits here, starting from bit 0 to bit 4, that called as a marks. Okay, so this marks here will determine your ADC channel. Which ADC channel that you point to use? There are 2 types of ADC channel. One is a single ended, the other one is differential input. Okay, in the next slide we will see what is the ADC single ended, what is the ADC differential input. Okay, last but not least is your ADLA. So this ADLA here used to determine either the left bit of the right bit of the result register inside your ADCH and the ADCL are used to store the result. Okay, whether you want to store the result from right to left or from left to right. Okay, so this ADLA here is to select lah. Okay, how you're going to store the data inside of your ADCH and ADCL, because ADCH and ADCL is 16 bit, we only use 10 bits. So the way you're going to store the data will be determined by ADLA. Okay, so this add marks, okay, register the register that I told earlier, this one here, from marks 0 to marks 4, okay, which is used to select the ADC channel. Alright, so the mark 4 to mark 0 will determine the analog channel and gain selection to be used. Okay, Okay, you have a two type of analog channel. One is single-ended, the other one is differential input. Okay, if a single-ended is selected, you can choose input channel among ADC0 to ADC7, which is a single pin is used as an analog line and ground as a common ground. Let's say lah, this is your sensors. Okay, one pin of your sensor is going to your ground. Okay, the other pin will connected to your ADC. Okay, let's lah. Okay, this sensor here is connected to ADC3. Okay, we're going to use a single ended lah. Okay, what happened is, okay, to do a programming, because this one is connected to ADC3, so in programming we need to put 0000001 to our at mark register at bit at location mark 4 to mark 0, so that the micropin know that you connect your sensor to ADC3. Okay, so this the value of a mark 4 to mark 0 depend on the sensor that you put to your ADC channel. Okay, so if differential input is selected, you can choose input channel as well as the op and gain. Okay, so you see here, this is the mark 40 option, value option that you can choose, and this is positive differential input and this is the negative differential input lah. You can put either way. Okay, and the gain that you're going to use, either you're going to use 10 times gain, 200 times gain, or without a gain. Okay, last but not least, the ADLA that I said earlier, okay, which is in bit find in ADMARC will determine the either the left bit or the right bit of ADC-H and ADC registers used to store the results. Okay, since our AVR Atmega 32 have a 10-bit ADC, alright, so only 10 bit is used, so another 6 will become used. Okay, so for this one here, if you put ADLA equal to 0, what happens is you want to going to do a right justify, means that you going to store your data from right to the left. Okay, if you put the ADLA equal to 1, okay, you're going to use a left justify, which is you're going to store data from left to the right. Okay. Okay, so this is the ADMARC register. Okay, the second register that we need to know is your ADC-H and DTCL register. Of course lah, this is your register to display your T-out. Okay, so ADC-H and DTCL used to store the result after the analog to digital conversion is complete. Every time you complete the conversion, okay, you complete conversion from analog to digital, it will be stored to this register here. Okay, again, because it is a 10-bit, okay, your ADC is 10 bits, so from this 16 bits data of ADC and ADCL, only 10 bit will be used, the other 6 bit will unused. So you need to make sure lah, either you want to going to store it right justified or left justified. Okay, next, the other register that you need to know is called as a ADC SRA register. Okay, so this one here is used to show the status and to control the ADC register. Okay, ADCs are also a bit size. Okay, they are a few bits that you need to know inside of this ADSR. One of them we call it as a ADEN. Okay, so this is your ADEN bit 7. Okay, so this ADEN here used to enable your ADC. Every time you going to use the ADC, make sure you put 1 to your ADEN. Put 1 to enable. If you not put 1 to enable, you cannot do the ADC. Okay, if you put 0 to ADEN, okay, you cannot do the analog to digital conversion. Okay, next is ADAC. Okay, so this ADAC used to start the conversion. Okay, every time you're going to start a conversion, make sure you put 1 to your ADAC, so the micropin know that you are going to start the conversion. If you put 0, okay, the conversion will not started. Okay, put 1 to start conversion. Okay, next is ADIF. Okay, so this is actually a flex lah. Okay, which is to show the status of the conversion. Okay, every time you complete the conversions, okay, every time the conversion is complete and the data register are updated, which is the data register here is your ADCH and ADCL is updated with your new DOut, the AD flag will go high. Okay, will raise. AD flag will become 1. Okay, once you start the conversion, okay, the FD is 0. After you finish the conversion, ADIF will become 1 after the ADCH and ADCL is updated. Okay, next is ADIE. Okay, this one also important. Okay, you need to know. This one here is interrupt enable, because for the ADC we are going to do interrupting. Okay, it is an interrupt. It is a one type of interrupt. Okay, so in order to use the ADC, you are going to enable this AD. Okay, because your ADC actually is one of the interrupt process. Last but not least is this last 3 bits here. Okay, so this last 3 bit known as a ADPS2, ADPS0, which is used to select the prescaler. Okay, to select prescale. Okay, this one is very important. Why it is important? Because you need to make sure that the conversion speed is acceptable. Okay, which is within the range. Okay, cannot going over the range that are required. If not, the accuracy of your conversion will lower. Okay, so this one here to make sure the higher conversion accuracy. Okay, so let's look at this ADPS2 bit, which is your prescaler option that you need, which prescaler the option that you're going to select. Right, so again, this bit here will determine the division factor between external frequency and the input clock of the ADC. Okay, there are few prescaler option available. All right. Okay, if you put 00, this is a reserve. Okay, you cannot put a 00. If you put 001, means that this one here you going to divide your ester by 2. 101, 010, you're going to divide it by 4. 011, you're going to divide your ester frequency by 8. 100, 16 prescaler, followed by 32 prescaler for 101. 110 is 64, and lastly is 111. You're going to use a 1 to 8 prescaler. Okay, so for the AVR, the DC requires an input clock frequency less than 200 kilohertz. Okay, so make sure that your F lower than 200 kilohertz. Why? For the maximum accuracy. Okay, cannot greater than 200 kilohertz. So that's why I told you earlier, the prescaler or the conversion time here is important, because you need to make sure that your frequency below than 200 kilohertz. Okay, let's look at some examples here. Okay, and AVR is connected to 8 MHz, so Ester sama dengan 8 MHz. Okay, calculate the ADC frequency for ADPS20, which 001, ADPS 100 and ADPS 111. Okay, first, let's look at the 001 of ADPS. So this one here, you use a prescale of 2. Okay, so let's find out what is your F. F equal to 8 megahertz USD divided by prescale. So you get 4 megahertz. Is 4 megahertz lower than 200 kilohertz? No, bigger. So you cannot use this one. Okay, so this one here, not valid. You cannot use prescaler of 2. Okay, next 100. What is 100? 100 with prescaler is 16. 100 prescaler ialah 16. So F sama dengan 8 divided by 16. So you get 500 kilohertz. Is 500 kilohertz lower than 200 kilohertz? Cannot. So you cannot use this prescale as well. Okay, let's put 111. 111, the prescaler of 111 is 128. Okay, so F sama dengan 8 megahertz divided by 128, you get 62 kilohertz. Okay, can you use this prescaler? Yes, you can use this prescaler. Why? Because it's lower than 200 kilohertz. What about, let's say we put our prescaler here is 64, which is you select 110. Okay, so F 8 megahertz bahagi dengan 64. Kamu akan dapat berapa ni? Divided with 54, you get 125 kilohertz. Can you use this one? Yes, you can use this one because the frequency is smaller than 200 kilohertz. So out of this, okay, these two here, between of this 1 to 8 prescaler, 64 prescaler, which one is the best? Which one that you're going to use? Of course you need to use 64. Why 64? Because this one is much faster, because T, okay, equal to 1 over F, because D is more faster than 1 to 8. Why? Because you see here, this 62 kilohertz, while this one is 125 kilohertz. Alright, if you divided you get your T, this one equal to 0.016 millisecond, but this one is 0.08. Okay, for the conversion speed, the lower the conversion, faster the conversion speed, the better the faster you get the result. So this one you get more faster compared to this one. So better you take a 64 prescaler.